Good morning, everyone. I am Xavier, and I am here to discuss about AC fundamentals. The things we are going to talk about is that what is an alternating system, the history and development of alternating systems, the generation of alternating EMF. So EMF is generated, not current. We're also going to talk about the equation E is equal to 2BLU sine theta. E sub m is equal to 2 pi BAN. We're going to talk also about the waveform terms and definition, the parts of a sinusoidal wave, EMF generation calculations, and the relationship between frequency, speed, and the number of pole pairs in an alternator. Good morning, everyone. So previously in our first semester, we talked about DC circuits. So these are circuits with DC excitation. So it means that all our sources were batteries and alike. So in circuits 2, we are going to discuss about the AC system. So before we discuss about the AC system, let's first talk about the history of AC. So the first alternator was built in 1835 by Hippolyte Pixii. So the first alternator was a device which utilized a magnet rotated by hand crank to produce AC. Now next was in the 1880s, the war of the currents was there. So in the war of currents, DC versus AC was disputed among. So the people behind the DC versus AC war was Edison and Tesla. So Edison was the first one who had to develop was the first one who had to develop commercial electricity, but it was in DC form. However, Tesla theorized and invented the AC system, which was found to be more efficient and is likely usable in major operations for electrical systems. Now, in 1880s, George Westinghouse bought patents for AC power transformers and motors from inventors such as Nikola Tesla. So, even though in this war, the AC system won out the battle. So because it was the most viable power distribution, and it is the way we transmit power today. Okay. So now we have talked about the history. Now let's talk about what is an alternating system. So an alternating system is a system wherein the magnitude of a signal varies in a repetitive manner. So for example, alternating voltage or current. So that's an alternating system. Now, why did the AC system won out during the war of the currents? So these are the advantages of the AC system. So first is that AC generators have no commutators. So it means that they are cheaper and they were much more efficient to use. They can also provide or develop electricity for as high as 33 kilovolts, and that construction and operating per kilowatt cost is low. Whereas in DC generator, capacities and voltages are limited only to comparatively low values. Second, AC can be bulkily generated or lowered using a transformer. So, which means that transmission and distribution of electrical energy is economical. Direct current use in transformers is not applicable. So that's why AC has an advantage over the DC. Next is AC induction motors are cheaper at initial cost and more efficient. So since AC induction motors are much more efficient, and in constant speed work, it's much more reliable than in DC generating motors. Next, high transmission efficiency of AC systems makes it economical. So since AC systems are largely distributed but economical. So it means that they are cheaper and much more okay. Next. 5. Switch gears for AC systems are cheaper. So switch gears are those circuit breakers, switches, and etc. So that's it. And next is maintenance cost of AC equipment is less. So yeah, these are the 6 advantages, and the list goes on. So these are the main 6 advantages of the AC system. That's it. Thank you. So we have these 2 pictures. So these 2 pictures represent how to generate alternating EMF. So first is that we can generate EMF by rotating a coil in a magnetic field. So this picture represents how a coil is rotated in a stationary magnetic field. So we have the north pole and the south pole of a magnetic field. So once this coil is rotated, so EMF is then generated. So if you connect a galvanometer here, so the galvanometer swings back to and fro because of the alternating EMF generated. Next is the rotating a magnetic field in a stationary coil. So this is an example. So you have here the stator. The stator is the stationary coil in this picture. So once the rotor starts to move, so this is regarded as the rotating magnetic field, and then EMF is then generated in this mechanism. So that's the 2 ways to generate EMF. Also, to generate EMF, there are number of cases that affect how much voltage is generated. So first is that the number of turns in the coil. Next is the strength of the field, or B. And next is the speed at which the coil or magnetic field rotates. So we shall denote this as N, and this one shall be N. N capital and N. So this is the speed. And number 3 is the speed of the rotating coil. So the number of turns is denoted as small n, and this one is big N. It's a rotation and magnetic field strength. So these are the 3 factors that affect how much voltage is generated.
Let us understand how an AC generator produces electricity. An AC generator is a device used to convert mechanical energy into electrical energy. It was originally designed by a famous physicist, Nikola Tesla. Working of an AC generator is based on the principle of electromagnetic induction. According to this principle, a change in flux linked to a coil induces an electric current in the coil. The direction of the induced current in the coil can be given by Fleming's right-hand rule. Lenz's law can also be used to find the direction of current in the coil. Let us now see the construction of an AC generator. An AC generator consists of field magnets, an armature, 2 slip rings, and 2 carbon brushes. The poles of field magnets are concave and cylindrical in shape, and therefore produce a radial magnetic field. Armature is a soft iron core on which a coil having a large number of turns of copper wire is wrapped. The 2 ends of armature are attached with 2 slip rings. These rings rotate with the coil. The slip rings are made of metals and are insulated from each other. 2 brushes are made of carbon. One end of each brush is in contact with rotating slip rings, and other end is connected to an outer circuit. A galvanometer is connected in the outer circuit to show the deflection due to the current induced in the armature. When coil is rotated between the pole pieces, a current is induced in the coil. The induced current is shown by the deflection in the galvanometer. The 2-way deflection in the galvanometer shows that the induced current is alternating. Now let's see the working of an AC generator. The armature keeps on changing its relative position with respect to the magnetic field as it rotates about an axis perpendicular to the field. Therefore, the flux linked with the coil keeps on changing with time. As a result, an EMF is induced. This in turn induces an electric current in the coil as the two ends of armature are connected to an external circuit. An electric current starts flowing through it. The current is detected by the galvanometer connected in the external circuit. Due to change in the relative position of the armature coil, the direction of the current flowing in each arm of the armature coil keeps on changing, and hence the current so obtained is alternating current. To understand the generation of alternating current more clearly, let us mark one arm of the armature as green and the other as pink. As per the Fleming's right-hand rule, the direction of current in the arm marked as green is outward, and in the arm marked pink is inward. After rotating half turn in anti-clockwise direction, the direction of current in green arm becomes inward, and that in the pink arm becomes outward. Thus, after every half turn, the direction of current changes, and as a result, alternating current is generated. If we plot a graph between the induced EMF and time, we will observe that the induced EMF shows sinusoidal behavior. It can be seen from the graph that the direction of the current keeps on changing with time, which again alternating nature of induced current.
So now we are going to discuss about the equations of alternating voltages and currents. So let us focus on this picture. So this is a rectangular coil having n turns and rotating in a uniform magnetic field with an angular velocity of omega. Now, let time be measured from the x-axis. Maximum flux is linked within the coil when its plane coincides with the x-axis. In time t seconds, when this coil rotates through an angle of theta, or we shall define this theta as omega t. So suppose it travels into this angle, so this is defined as omega t. In this deflected position, the component of the flux which is perpendicular to the plane of the coil is measured as phi is equal to phi m cosine omega theta. So as the coil rotates or revolves around this area, so it produces a magnetic flux which is equal to phi sub m cosine omega theta. Now, since I hence flux linkages of the coil at any time are n phi, which is equal to n phi sub m cosine omega theta. Now, according to the Faraday's law of electromagnetic induction, the EMF generated is given by the rate of change of flux linkages in the coil. So it means that when theta is equal to omega t, we define electromagnetic induction equation at d over the time derivative of n phi. So from this equation of electromagnetic induction, we substitute. So this is n cosine wt. So E is equal to n, since n is a constant, n omega. So the derivative of cosine cosine omega t is equal to negative sine t omega t. So the negatives cancel out each other, and this is our induced voltage equation. So now, when the coil has turned 90 degrees, so when theta is equal to 90, so sine omega t is equal to 1, which is equal to sine Okay, so in this equation, we will substitute omega t in 90. So since sine 90 is equal to 1, therefore omega n phi is the maximum induced voltage. So, or in short, we can say this, that the induced voltage is equal to 2 pi f, which is equal to omega times n, and since flux is equal to magnetic field times area, so B A. Also, this is the maximum magnetic flux. So this is our final equation for magnetic voltage induced. So this is our final equation for the maximum voltage induced in the rotation of a coil. Now let's talk about an alternate method for the equations of alternating voltages and currents. Now in this figure, it shows a rectangular coil AC having n number of turns and is rotated in a magnetic flux of density B. Now let the length of each side's AC be in L meters and their peripheral velocity be m meter per second. So rotation is now expressed in meters per second. Let angle be measured from the horizontal position also. So the reference angle for angle measurement is the x-axis. Now if this coil rotates through the magnetic flux and it parallels with the y-axis, no flux is cut, meaning no EMF is generated. However, if it lies in an angle not not parallel to the magnetic flux, EMF is generated and flux is cut. Now, there are two ways of resolving its components. So when the coil has turned through the angle theta, its velocity can be resolved in two ways. So the first one is the v cosine theta component, which is parallel to the flux direction. So as you can see, if this one is satisfied, no flux is cut, so meaning no EMF is generated in the v cosine theta component. In the second one, v sine theta component, so it is perpendicular to the flux direction. So if the coil is perpendicular to the flux direction, flux is cut. Flux can be cut and voltage or EMF can be generated throughout the rotating coil. Now, we shall define a new equation for an alternate EMF generated in both sides of the coil. So this is referred to as E 2B N L V sine theta. So B here stands for the magnetic flux density measured in Tesla. N is the number of turns the coil has. L is the length of the coil. And V is the speed of the rotating coil. Now this is the equation for the EMF generated in this alternate method. So now E has a maximum value when theta is equal to 90 degrees. Now, hence from the original equation, E sub m equals, from this equation, E sub m 2b n LV is satisfied when theta is equal to 90 degrees. And also, when theta is 90 degrees, this can be rewritten as E sub m is equal to, this can be rewritten into E sub m sine theta. So both methods are the same. So from our previous equation, we have this one. So we have this equation. We shall define this, since this is in maximum term, we shall define this as the maximum voltage or EMF induced. So E capital sub m is equal to 2 pi f, and Bm and B sub Ma. Now, substituting this value from the original equation, when sine theta is not maximum, so we have 2 pi f n b sine omega t. So substituting this equation, E is equal to E sub m sine omega t, or E is equal to E sub m sine theta. So at any angular frequency of a coil, so this is the equation for the induced voltage. Similarly, for equation of induced alternating currents, we have I is equal to I sub m sine omega t. So this works as well as for currents. Waveform terms. Now, a waveform is a variation of quantity such as a voltage or current shown on a graph like this to a base of time or rotation. So you have E or I versus time graph. So this is a waveform. Now, cycle. So a cycle is the each repetition of a variable quantity recurring at equal intervals. So from here to here, from this point to this point, this is regarded as one cycle. Now, for the period, so the period is the duration of one cycle, so its unit is in seconds. So the time the signal started from here and then ended from here, that is called the period or the time period of a cycle. Next is the frequency. So the frequency is the number of cycles that occur in 1 second. So we can say that frequency is equal to 1 over t, which means that its unit is in cycles per second. Next is the amplitude. So the amplitude or the peak amplitude is the maximum instantaneous value, either positive or negative, of an alternating quantity. Say for example this waveform. So our amplitude will be this peak. This is the amplitude. So this is the positive amplitude and this one is the negative amplitude. So that's it. Good morning everyone. So we are here to discuss about the relationship between the frequency, the number of pole pairs, and the speed of rotation in an alternator. Now consider a coil rotating at a speed n RPM in the field of p poles. So as the coil moves past successive north and south pole, one complete cycle is generated. So say for example, our cycle starts at the north pole and then finishes at the south pole. So once it starts at the north pole, it is located in this part of the graph, and it ends at the south pole and is located in this part of the graph. So one complete cycle is generated in one rotation. Now, we have the equation F is equal to P times N over 120, where F denotes the frequency of the rotation, P is the number of pole pairs in an alternator, and N is the speed of rotation of the alternator. Okay, so consider an alternator which has a number of pole pairs of 8 and the speed of rotation in 1,500 RPM. So to get the frequency of the alternator, we have to directly substitute from the formula F equals Pn over 120. So that's 8 poles, that's 1,500 RPM over 120 we get a frequency of 100 Hertz. So this is the frequency of the alternator. Now, if you wish to find other element of the formula, so you have just to manipulate the formula. So to get P is equal to 120F over N, or to get N, that's 120F over P. That's it. In a magnetic field having a uniform density of 0.05 Tesla, the axis of rotation being at right angles to the direction of the flux, the mean area per turn is 40 centimeters squared. Calculate the frequency, the period, or the time period, the maximum generated EMF, and the value of the generated EMF when the coil has rotated to 30 degrees from the position 0 EMF. Now, so first, we have to take note of the data given. First is that we are given N, or number of rotations per minute. So N is equal to 1,500 RPM. And then we have magnetic field density of 0.05 Tesla. The area, which is at 40 cm squared. Yes, that's it. So, first, we have to find the frequency. So, the frequency is given by the equation F is equal to 1 over T. Now, for 1 over N. Oh, yeah, okay, so A. So, the frequency must be given in number of cycles per second. Since the given N is in RPM, we have to convert it to CPS, or rotation per second. So to convert this, we have 1,500 rotation per minute times 1 hour for 1 cycle times 1 minute is equal to 60 seconds. This is equal to 25 Hertz. So this is our frequency. Next, we have to find the time period. Since the time period T is given in seconds and is given in the equation T is equal to 1 over F, we have to directly substitute this value. So 1 over 25 Hertz, this is equal to 0.04 seconds. So this is the time period. Next. So to find the maximum generated EMF, we have to consider the equation E sub M is equal to 2 pi F N and A B. So, since we have F as 25 Hertz and at 1,500 RP, okay, so to find the maximum generated EMF, consider the equation E sub M is equal to 2 pi N A B. So N is the number of rotations per second, number of rotations per minute, or we shall express this in CPS. This N is the number of turns, and A is the area of rotation, and B is the magnetic flux density. So substituting the values, we have 2 pi times N, which is 1500 over 60 times N, which is 100 turns, times area, which is 40 centimeters or 0.004 square meters, times 0.05 Tesla. So the maximum generated EMF will be equal to 3.14 volts. Next, so we have to find the value of the generated EMF when the coil has rotated through 30 degrees in the position 0 EMF. Using the equation from C, we have to put sine theta since it is positioned at the exerted angle. Now, since this has a value of 3.14 already, so we can multiply sine 30 directly from it. So EF at 30 degrees will be equal to 3.14 volts times 0.5, that is equal to 1.57 volts. This is the answer for letter B. That's it. So good morning everyone. So let's proceed with our problem number 2. A square coil of 10 cm side and 100 turns is rotated at a uniform speed of 100 rpm about an axis at right angles to a uniform magnetic field strength of 0.05 Webers per square meters. Calculate the instantaneous value of the induced electromotive force when the plane of the coil is at right angles to the field or in the plane of the field. Now, let us analyze what does A mean, so at right angles to the field. Now, let us consider our coil to be in a shape like this. So, if it says at right angles to the field, it will form perpendicular to the magnetic field. So, our coil should look like this. So, it means that theta will be equal to 0 degrees. So, solving for A, we have, since theta is equal to 0 degrees, and we have the equation E sub m is equal to 2 pi B N F A. That's it. So, sine theta. Sorry. So this is the equation. So as you can see, we have already set a value for theta, which is 0. Yeah. And since sine 0 is equal to 0, so E sub m will be directly equal to 0. So the answer for letter A is that no EMF is generated. So that's 0 volt. So next is letter B. Now, what does in the plane of the field means? So it means that the coil is parallel to the field, to the magnetic field. So the coil forms like this. So it means that our second angle will be equal to 90 degrees. So since sine 90 is equal to 1, directly substituting from the formula, that's 2 pi times 0.5 Tesla or Webers per square meters, 100 turns, times F, since F is equal to 1 over N, that's F is equal to N, or that's equal to 100 rotations per 60 seconds. So that's 50 over 3. CPS times area, which is 10 squared centimeters squared times 100 cm 1 square meters times 1. So our E sub m is equal to 52.3 volts. So this is the EMF generated in letter B. So this means that at angle 90, generated EMF E is equal to E sub m, or the maximum. So this is the maximum available generated voltage.